All right, welcome back, everyone. Kind of winding down here. Probably just one more kind of lecture-y week, I think, right? And then we have kind of a free play session for the last Tuesday of the semester. So, and I think today's going to be pretty low-key. We kind of spent a long time going a bit in depth last week with the McGurk demo, just kind of making sure, hopefully you guys understood that a little bit better. So we didn't quite get to the picture version of that demo that I wanted to get to also last week. So I think today we're mostly going to just focus on finishing up the dynamic stimuli stuff, where we can see how you can use Matlab to kind of change your stimuli and create new stimuli and things like that on the fly. As you guys have seen, there's some of that on the problem set, so hopefully that is making some sense to you, and hopefully it will make more sense to you after today. And I think next week we'll go ahead and, so today I think we'll just finish up the dynamic stimuli stuff. I did a demo of doing a little data analysis in Matlab, but I think we'll probably save that for next week and roll that in with a little basic plotting, but nothing too intensive next week, and call that a day, because you guys have learned a lot so far. I don't want to break your brains in these last few weeks, so I think we'll keep it to a minimum. So this next problem set, well, talk about that. Current problem set's due Friday. Hopefully you guys are doing all right with that. Problem set 10 will be released on Friday. There won't be a ton of new stuff on the last problem set. I think it'll mainly be kind of extending what you did on the previous problem sets, but really just demonstrating the same MATLAB skills in new ways. Because as you've seen, there's not a whole lot of, I've kind of given you some demos of how to show stimuli and things with Psychtoolbox, but there's nothing that's incredibly new. If you know how to play a sound and put up a picture, then it's really just like about deepening your knowledge of tips and tricks of the trade and so forth. I'm working as fast as I can on marking the previous problem sets. I will send those out as soon as I have them. Projects are due on the 2nd of May. Again, so we've talked a little bit about submission. I mean, I think the plan for that will be to basically just zip up whatever files are required to run the project and send them to me via the Gmail address you've been sending in stuff with. I think that makes the most sense. But also, almost certainly you will need to include some kind of brief release notes along with the actual code saying, like, here's what you need to run, here's how like this, basically the readme .txt file for your software. And with that you can say, like, okay, well, these are the bugs that I still haven't fixed, just kind of like real software, right? These are the bugs I haven't fixed yet. These are the features I maybe didn't add, or something seems to not do quite what it's supposed to, or if everything works great, it's just a quick rundown of what you can do if it's not totally obvious from the program. So I think we'll just plan on doing it that way, and then maybe, we'll see how stressed you guys are. We can talk about this in a week or two. After you've submitted them, if you guys want to have a quick informal meeting one day for like an hour where everyone shows off their projects. That might be kind of fun if you want to show them off, because I didn't want to make you guys do presentations because that's more work. But if people want to just get together for over lunch or something like that one day, or in the evening, and just spend a few minutes demoing what you produced, that could be fun, I guess. And I can show off my project if I ever get any time to work on it myself. Okay, any other stuff from you guys? Any questions or anything? Everybody good? Okay. So this is the demo we left off on last week, which I think we pretty much got to the end of. So what we're going to work on today is getting into this last demo, which adds a couple new features to this McGurk effect study. So remember what we were doing before was we were doing this dumb little demo where we blended two sounds together and then put some text up to see if the text influenced our perception of the sounds. And it didn't seem like it did very much, right? But if we want to go back to the roots of the McGurk effect, remember the idea was if in the original McGurk effect, if I show you, I always mix up the syllables, if I show you, what is it, someone saying ba, right, but show the lips saying ga, what you hear is da, I think. Is that right? Something like that. I should look that up again, right? But that's the basic idea, right? So maybe we'd get a better McGurk effect if we actually showed these mouths pronouncing the syllable. And if, I don't think we'll have time this week, but next week I'll let you know. I actually worked up a demo that's a little bit better calibrated than the one we're going to do today and ran it on myself. And there is some effect of, at least if you show the video of a mouth producing syllables. I haven't tried it with just the text yet, actually, because I think the text is probably not a strong enough stimulus. But we'll see. I could do that too. But today what we're going to try is we're going to try to go back to the roots of the McGurk effect and try to make a little animation, basically, of a speaking mouth, right? So what we could do, of course, if we wanted to be lame, is just record movies of people speaking the various syllables. But it might be a little bit more interesting to animate some things for ourselves. So that's what we're going to try. So in a somewhat unusual move, to help you out with your problem sets, as you may recall, I sent you, last week sometime, I sent you actually all the files we're going to create today. Now, I don't think it's very helpful to learning if you just kind of open those up and run them, although you might have already seen this demo in action. But so what I think it makes sense to do is kind of go through, start with the previous demo, and then build up to the one with the animated mouth talking.
God.
Yay. All right. So it works, right? Okay. I'm just cleaning up everything from forcing that to quit. Okay. So that's our task, our old demo. What we're going to try to do now is we're going to try to bring in those creepy animated faces, though. A, because that's cool, and B, because it can teach you a little bit about doing this dynamic stimulus thing with images. So the other thing that we're also going to do, actually, and maybe we'll do that first, is we also said, well, maybe this task will be a bit harder, and it'll be thus influenced a bit more by the image or the text if we degrade the stimulus a little bit, right? Because this is often something you want to do if you want to lengthen reaction times or just for various reasons make a task a little bit more difficult. One thing you can do is degrade the stimulus, right? So this is in your problem set to do with a picture, but we're going to do this with noise now, where we're going to add a little bit of white noise to the sound that we're playing to make it a little bit harder to discriminate, right? Because it's still a little bit too easy to distinguish your ba's and your ga's and your da's. So maybe let's do that first, and then we'll turn this from a text-based McGurk task to an actual picture-based McGurk task. Okay, so what I'm going to add in here, first of all, so you remember last time we talked a bit about the proportions of how we blend these sounds together, right? So what we decided is we're going to pick 2 syllables on each trial, like ba and da, and then we're going to, if we picked ba and da, then we might make the sound that we actually play 52% ba and 48% da, right? But let's also now add in a little bit of noise to this just to make things interesting. So I'm going to define a variable I call noise percent. Now it's really not a percent, it's a proportion, because percent would be 10 without the decimal point, but we know what we mean. All if you want to be proper, you can do that. Okay, so we're going to define and say, let's add in 10% white noise to this sound, right? So every time we play it, we're going to add a little burst of noise to what we play. So the question is, where would we add that in? And we probably want to do it down here, right, where every trial we go through, we pick 2 sounds right here, and we blend them together in some proportion, right? And we talked a little bit about how to do that. You literally take the sound wave for the first sound, multiply that by like 52%, right, to make a sound wave that is 52% of the volume of the original sound. Then take the second sound, multiply that by 1 minus that, so that'd be 48%, to create a sound that's 48% the amplitude or the loudness of the second syllable, and then you add those together to make one whole sound again, basically. That is essentially those two sound waves. And you see, by the way, this is something that maybe is not super obvious, but if you want to blend two sounds together, all you do is add them together, right? And that's a pretty easy thing to do. Okay, now there are a few, like if we were doing this for real, there are a couple other things you'd probably want to do, but for the moment, let's say that's all you have to do. Okay, so let's add some noise in. So we're going to do that. So basically noise, if you talk about noise in an image or noise in a sound or whatever, right? Noise is just random information, right? That's non-informative. So noise is really just random numbers, right? So essentially what we're going to want to do is we're going to want to create a sound wave that's all random numbers, and then add some proportion of that random number sound wave to the sound wave that we're playing, right? So what we can do is I'm just going to make a variable called this noise, right? Now one thing that we have to know is sort of what the range of numbers is in our sound wave, right? Because we weren't really worrying about that before. So if we go back here and we do, let's see how our wave read function works again. All right, so let's call this sound wave sampling frequency and bits equals wave read. Just as an example, let's read in the ba.wave file. Right? Remember we did this a couple lectures ago, I think. And we have this sound wave, right, which we can, again, a quick forecast of our Matlab plotting demo. You can call the function plot. You just put the sound wave in your plot function and get a line graph, essentially, of the sound wave, right? And again, if you've ever looked at a sound wave before in a sound editing program, that's what they look like. So sound wave diagram is really just a line graph of a bunch of data, right? So the key thing to note here is the range of values. And in MATLAB and in life in general, typically the way that sound is represented is values between -1 and 1, right? So this is a little bit different than some of the picture representations, which there's that whole thing in the problem set about the uint8 format, which can only be 0 to 255 and so forth. But sound data are just going to be numerical values, right, between, you see, silence is 0, right? And then the values look like they can go up to, they don't quite go up to 1 or -1. They actually go down to about -0.6 or +0.6. But in theory, the maximum values are -1 and 1. So basically, if we want to add some noise, we want to add some random numbers in the range -1 to 1, right? Now you guys, by now, hopefully have used the MATLAB rand function a couple of times. What range of values does the MATLAB random number generator give you? What's the minimum? 0, and maximum is 1. So if I want to transform a random number given to me by MATLAB from the range 0 to 1 into the range -1 to 1, all we have to do is say, all right, well, we can multiply that by 2, right? That gives us a random number from 0 to 2, and then subtract 1, right? And then we'll get some random numbers, hopefully, that range between, right, between -1 and 1. So that's for a single random number, but of course what we want to really do is create a long string of random numbers the same length as the same size as our sound wave, right? Because what we want to do is add a little noise to the whole sound wave. So what we're going to do is just generate some random numbers. Do we have a variable for this already? Let's see if we do. A variable, no, I don't see it. A variable for the overall length of our sound wave. So what we can just do is say, let's create some noise, so a random number, and remember, when we call the rand function, if we give it some values like 5 and 2, that'll give us a 5 by 2 matrix of noise, right? Or 1 by 10 or whatever, right? So if we want some random numbers the same dimensions as our sound wave, actually, and this is a little trick, we can just say a random number and put in the size function and that'll tell it to give us a random number matrix, the same size as our sound wave, right? So that'll give us a set of random numbers, the same size as our sound wave. And then, of course, to transform it into the range -1 to 1, we say we multiply by 2 and subtract 1. That's going to give us a random burst of noise ranging between -1 and 1. But of course, we said we want only like a 10% noise factor. So what we can do is say this noise equals this noise times, what do we call it, noise percent, right? So that'll make it 1/10 as high. And then what we of course want to do is say this sound equals this sound plus this noise. All right, so that will take the blended sound wave and add it to the noise that we just generated of the proper volume and create a sound with noise in it. So if we want to see that kind of in action on the command line before we see it in the script, let's try it here. So we have this sound wave, right? So here's the sound wave. And if we play it, let's see, Matlab's is called, sound. So if we say, just to avoid bringing in Psychtoolbox, we can just say sound wave, sampling frequency.
Ba.
All right, so there's our ba, right? Now if we want to make some noise, so let's call it like my noise or something like that, equals a random number, the same size. Here we called it sound wave, right? So we'll get some random number, same size as our sound wave. And I'm actually going to turn the volume down for this, because this is going to be really obnoxious. If we play the noise alone, well actually first let's maybe plot our noise. So that's what noise looks like. It's just random numbers basically, so it just kind of spans the whole range. It doesn't look like a sound wave. And if we play, instead of the sound wave, if we play my noise. All right, everybody hear that? It's noise, not much to hear. That's what random white noise sounds like, right? And if we want to make it a little quieter, we can say my noise equals my noise times 0.10, right, which is what we're going to do in the script. And if we play that, it's much quieter. I'll turn up the volume again and you might be able to hear it. All right, everybody hear that? But it's much quieter than it was. So now if we want to say, if we want to make a new sound, so let's call this like sound wave 2, and we want to just add our old sound wave plus my noise. So let's plot the old sound wave, which looks like that, right? And then maybe, it's probably going to mostly overwrite it, but let's try on the same graph, in red, plot the noisy sound wave. Yeah, I mean, it mostly overlaps the other one, right? But you can see it's kind of a little fuzzier, basically. And if we play it, let's see, sound wave 2.
Ba.
All right, so you hear the noise plus the ba, right?
Ba.
So it's still pretty easy to hear ba in this case, right? Because it's an unblended syllable, it's just ba. Now, if we wanted to add more noise, it would be harder to hear ba, right? So if we wanted to say my noise equals my noise times 5, so get that up to like a 50% noise again, and say sound wave 2 equals sound wave plus my noise. This might be a little bit obnoxiously loud on the podcast. And now play it with 50% noise.
Ba.
All right, a little bit harder to hear, right? Because the noise is louder relative to the sound. Okay, so now let's try this in the actual script. Hopefully, those few lines of code we added should be enough to make it noisy and make the discrimination a little bit more difficult. Hang on a second, I might crash Matlab here. Good, I think I avoided it. There's this weird bug in this version of Matlab where like sometimes figure windows don't close and then they cause it to crash. All right, so this should be just like before so far, but with noise added, right? So making the discrimination slightly more difficult. Again, watch out for loud noises on the podcast.
Ga.
Okay, I think that was a ga.
Ga.
That was a ga.
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 I think that was a da.
Ga.
I think that was a ba. Okay, you get the point though, right? So, okay, so that makes it a little bit more difficult. And again, what you guys are doing in the problem set is basically that same thing, but adding visual noise instead of auditory noise, right? So it's kind of, I mean, not to give too much away, but it's kind of the same idea, right? Like you add some random, if you wanted to see visual noise, right? If I want to make a 200 by 200 pixel picture that's just random noise, looks like that, right? So yeah, I made some random noise. Now I pulled a little trick there. I told you, I think, in the problem set that your noise or your images have to be in uint8 format, and actually sometimes they don't. Sometimes Matlab can use information in an integer format, or sorry, in a double format, and that'll be okay. But in the problem set, it's better if you stick to uint8. So really, the proper way for me to make a noise image that's a uint8 format is to say my image equals a 200 by 200 grid of random numbers times 255 and make a uint8 out of that. I'm probably giving you too much information for the problem set now. Right, and it's still a noisy image like that, but now it's in uint8 format the way it should be. All right, so you see that? Nice and noisy. Should have grayscale values all over the grayscale spectrum. If you want to make colored noise, which I know we all do, you basically have to make, instead of having a grid of numbers that's just two-dimensional, you have to make a three-dimensional grid of numbers where it's 200 by 200 by 3, because basically you need a red image, a blue image, and a green image, and then those are overlaid to make a full color image. So if I wanted to say my color image, hell, we're programming, so use American spelling. So let's do rand 200 by 200 by 3, oops, times 255, and make a uint8 out of that. In theory, let's see if I did this right. All right, so now we've got color noise. Yay, pretty. Sparkly kind of, right? All right, so that's color noise. In the problem set, you only have to do black and white noise. But if you wanted to do random colors, clearly that's how you could do random color noise, right? Okay, but anyway, that's getting a little bit beside the point here. The main point is that we got our noise working in the script, right? All right, any questions so far? All right, so let's start to add in some picture stuff now. So we're going to, now this is going to be a fairly major change. So we're going to kind of go through a bunch of stuff before we can actually see it in action. The key things to note here are, if you see how I set this up, I downloaded these pictures and I would love to give them credit, but now I've forgotten the website. So maybe I'll give them credit somewhere if I can find it. But there's some demo on the internet, an animation demo talking about, you know, if you're animating a movie like Shrek or The Incredibles or whatever, you know, some kind of animated Pixar type movie, you know, they have to obviously make the characters' voices appear to sync up with the voice actors' audio, right? So it's just basically a demo page of like these rendered mouths and showing them in various syllable positions. Now, what it turns out is that apparently this is what your mouth tends to look like when you say ah. I guess you guys can look at me while I say ah and see if you agree. Here's what your mouth is usually looking like when you go buh, right? So here's an ah and a buh. And in theory, you know, if you're animating this, you know, with your fancy 3D animation software, you could actually, model the lips opening and revealing the teeth and so forth. I don't have those intermediate stages of animation, so what I decided to do in this script was just sort of do the cheapo version of this animation, which is to just mix these two images together and kind of fade one into the other rapidly. Okay, so if you go B and fade into A very quickly, maybe it looks kind of like Ba, right? And then the same for apparently D, looks like that, D, with the teeth together. And actually, here's a little bit of a cheat, is that apparently G also looks like D. When you G, D, G, D. I guess you don't have to change your mouth posture too much. So one thing that's a bit weird is it's actually the same image for G and D, but for our purposes, it should be okay. So what we're going to try to do here is replace the text just saying ga, ba, or da while we play those ambiguous sounds with an animation of a mouth actually doing that, right? And you guys have seen from the fact that I gave you the code already that this will work. We're going to kind of step through and figure out what that code actually does. So the first thing I'm going to do is just define some new variables. And I encourage you guys to follow along here. So again, we're using these cell matrices, right, to make a list or a matrix of 3 strings, right? And I'm sorry, guys, I haven't been very consistent about my notation. Really, they want you to kind of separate things with commas, although, as you can see, it doesn't really matter. It works the same either way. So I called that cell consonants, right, because it's a list of our 3 consonant images. And our vowel image, let's call it consonant images, actually, just to make it clear. And the vowel image equals ah.png. So that's just telling the script what our stimuli are called. Let's see, I think the only thing to change here is we change read the word to watch the image or something like that and listen to the sound. Then select the choice that best matches what you heard. So change the instructions just a little bit. We're going to record our responses the same way, right? Display the possible responses the same way, that's fine. Text color is the same. So one thing we're going to need to do is we're going to need to define how quickly we transition between these images, or how long they need to stay on screen. Well, let me back up a bit. What I wanted to do, what we want to do ideally probably, is animate the moving mouth to take the same amount of time to display itself as our sound takes to play, right? So when the sound plays ba or da, or really ba and da blended together, right? What we don't really want is we don't want to hear ba-da, and then see the mouth go ba, very slowly. Or conversely, we don't want to go ba, or have the mouth go very quickly and then have ba come out slower than the mouth, right? Because then you look like a dubbed movie, and it doesn't, it doesn't give you the illusion that it's actually working, right? So ideally, what we want to do is figure out how many seconds long our sound wave is, and because we already did this last time, we've adjusted our sounds so they're all exactly the same length, right? And we want to say, okay, in the time that sound is playing, we want to go from frame 1 of whatever syllable we're animating. So frame 1 would be 100% the consonant, and presumably we want to end up on a frame that is 100% the mouth in the ah position, right? And then have some number of screen frames in between, which are various steps of blending between those two extremes, right? And of course, how many steps there are in that amount of time that the sound is playing sort of depends on how quickly our screen is refreshing. So there's ways to have Psychtoolbox figure out for you how quickly your screen is refreshing, but because it gets a little complicated with multiple monitors and stuff, what I'm going to do is I'm just going to type it in here and say, I know that my refresh rate is 60 hertz, and I think probably all of your LCD screens are 60 hertz as well. If I were doing this on a CRT monitor, like an old school, like big monitor, with a glass screen and everything. I could probably crank up the refresh rate to 60 or 75 or 85 hertz and get a smoother animation, but this is fine for now. Okay, so we have to tell it the refresh rate. There's a few other things we're going to add in, but we may not add it in right this second. So let's leave it at that for now. Okay, so because what you may have seen is in the full version, I decided to make the animation a little smoother if we blurred all the images a bit, but that can come later. Okay, so let's go down here. So we're going to load in our sound files, equalize the sound lengths. And then what we can do actually, so after we've equalized the sound lengths, right here, let's figure out like number of animation frames, right? Because now that after we've read on our sound files and equalized all their lengths so that we can blend them together, we now know how long each sound wave should take to play, right? So we can use this to figure out how many frames of images we have to show. So what we can do is figure out our sound duration. And again, you guys have this code, I realize, but we may make some tweaks as we go, so it's good to kind of type with me, I think. And let's see. Let's see, somewhere here. Oh, we already have our max sound length, right? Now that maximum sound length, remember, is going to be in samples, right? Or remember, sound waves are a certain number of samples per second. So typically CDs are 44,000 samples a second. This audio is 22,000 samples a second. So if our sound length is 22,000, that's a 1 second amount of audio, right? So what we need to do if we want to turn the duration into seconds, we take our maximum sound length and divide it by, what do we call our sampling rate? We call it sampling rate. Oops, sampling rate. So that gets it in, now this unit is going to be in seconds, right? So if we divide the length of the sound file data by the sampling rate, we have how long it is in seconds. And from that, we can figure out how many frames, in other words, how many video frames are going to be in that amount of time by saying, all right, well, if it's 60 frames a second, that's going to be the sound duration in seconds times, what do we call times our refresh rate, right? So, if our sound duration was 1 second, that would be 60 frames. If our sound duration is 0.5 seconds, that'd be 30 frames, and so on, right? And what we're going to probably want to do is round that to a whole number because you can't have a non-whole number of video frames, obviously. You have to either show it or not. You can't have half a frame. And here's a little tricky bit of magic. So this is a line that'll take a little bit of explaining to do, I think. So maybe I'll work this out, and then maybe we'll then take a break and put this into action in the next half. So the line that you may have seen if you have this code in front of you is this. So I call this variable image proportions. And basically this is what this is saying is on each frame, what proportions to blend together our two images in, right? And I have this kind of weird, funky code here that says 0:1 over in frames minus 1:1. Okay, that's a crazy line of code there. So let's break this down a little bit. So first of all, we have seen before things like this, right? I think I've shown you multiple times. We use this in for loops. We use this when we want to make new matrices. If I do 1:10, what that gives me is the numbers from 1 to 10, right, by ones. What I can't remember if I've shown you is, let's say, and this is similar to Python's range function, right? And I think also similar to the range function, if I recall correctly, we can specify, actually, if we want to, different step ranges that we want to do. So if we want to not just do the numbers, the integers 1 to 10, let's say we want all of the even integers, from 2 to 10. We could put another number in the middle and use 2 colons, whoops, well I did it 2 to 20, but that's fine, and get 2 by 2s to 20, right? So that's what this notation means, is if you have number, colon, number, colon, number, it means what the lower value is, what the upper value is, and what the step in between those values is. Everybody cool on that? That makes sense to everyone? So if I want to do something like, say, I want to display, 0% of image 1 the first time and 100% of image 1 the last time, and go in 10% increments, what I can do is I can say 0, maybe it'll be good if I space it out a bit, 0 by 0.1s to 1 gives us 0, 0.1, 0.2, 0.3, 0.4, 0.5, right? So you can do this with decimals as well. Now it's worth noting that, one nice thing about Matlab is it doesn't force you to get these exact. So if I wanted to do like 2 by 2s to 19, it's not going to complain and say that you can't make 19 by adding 2 to 2s. It's just going to stop at the lowest number, or the highest number less than 19 that goes by 2s, right? So that's kind of nice. But in this case, what we really wanted to do, right, so you notice that when we did this, let's go back to this one, 0 by 0.1s to 1. So what that's saying is, if I had 2 images and I wanted to say use 0% of the first image, and then by logic, 100% of the other image, 10% of the image 1, 90% of image 2, 20% of image 1, 80% of image 2, and so on, right? I went from 0 to 1 in steps of 0.1, right? And how many numbers did I end up with? Should end up with 11, right? Well, you see it here, right? So there's 11 values here, right? So if you go from 0 to 1 by tenths, you get 11 values, right? So the question is, if I want to go from 0 to 1 and I have like some weird number of frames, so let's say I have like 17 frames that I want to display, and I want to work out the percentages, like if I want to have 17 steps, right, between 0 and 1, essentially what I'm going to want to do is have 0 on one end and 1 on the other end, right, because that's full one image and full the other image, and then go by 16ths, right, because here I went by tenths, and there are 11 total steps, right, because you know what I mean, like if you consider like counting from 0.1 to 1.0 by tenths, that's 10 steps, and then you've got an extra one for 0, right? So let's say I have 17 frames I want to fill. I want to go by 16ths, right? So if I went from 0 by 1 over 16, which is a 16th, to 1, that would give me 17 numbers, right? 0, 0.065, 0.1250, and so on. Everybody cool with that? All right. So that's basically what this line is doing, right? So we're basically, if we break this out a bit, we're going from 0 to 1, and then basically the number of frames minus 1. So if we had 17 frames, this would be 16, number of frames minus 1, and then 1 over that, right? So we're going from 0 to 1 in whatever tenths, depending on how many frames we're going. All right, is that cool with everybody so far? Everybody everything kind of making sense so far? All right, so maybe we'll take a little quickie break. So yeah, so let's start up again, get to the end of this demo so that we can show you how to do like a little kind of dumb animation here. Well, actually, it's not that dumb, right? Because it's not true animation, but this is actually more sophisticated than if you were just showing animation. Like you could easily load in 10 separate images and just show them in sequence, right? So we're doing something a little bit more sophisticated here, where we're actually going to load in images and then kind of blend them together to make our own kind of animation-ish, right? So it doesn't, in the end, it's more of a fade than a real animate, but it's actually more sophisticated because hopefully if you guys can do this and work this out, it would be pretty easy for you to see how you could actually animate something. And of course, just like Psychopy, Psychtoolbox has functions built in that actually will play, movie files and things like that in certain formats. So you can always just make a movie. But it's good to know how to, do things like this, because you'd be surprised how often this stuff comes up if you know how to do it. Like, especially if you do visual perception stuff, you're having to figure out how to kind of animate frames of things on screen all the time. And what I was starting to say is, of course, keep in mind that, once you guys know how to do a little of this stuff, you can do to a sound or an image file or an image that you're going to display on screen anything you could do to any matrix, right? So with a little bit of thinking, there's a lot of manipulations you can do to images. So you can, feel free to play around with this stuff, and I can show you some things, if we have time, that you could kind of do, if we have time for it. Okay, so let's go on now. So what we did is we figured out just now this image proportions matrix, right? Or it's really just a list of numbers. And that's going to tell us how much of each, the consonant image versus the vowel image to use on each frame of our animation, right? So of course now the thing we need to do is, actually, instead of just putting up a boring bit of text, we actually need to figure out how to put up these images and display them, right? So let's see where we want to do that. So we've got, before we display our instructions, we probably want to go ahead and actually read in our images here. So let's do that actually, just so we'll have them read in, because it's easier if we just read them in once, and then we don't have to read the files in the middle of our task. So what we'll want to do is let's make a little for loop. So go from 1 to the length of our consonant images matrix, right? Because we'll want to read in 3 consonant files. But of course, again, we're trying to make this code nice and general so that if you wanted to add in a 4th consonant, you wouldn't really have to change anything but the stuff at the top of the script here. You could add in like, fa and add an f.png, and you're pretty much good to go. And you'd have to add in another response key and stuff. But we're trying to make this code nice and general, so we'll just go through the length of our consonant images, even though we know it's likely to just be 3, right? And let's make another cell matrix that has, let me actually see where I make this. Okay, yeah, that has basically the image information for our 3 images in it. So just like we read in kind of the analog here of where we read in to our sound cells, we read in all of our sound data. Let's now read in our image, our 3 images of data into an image cell. So let's call it consonant image cell. So let's call it consonant image cells, I guess, to distinguish it from the names of our consonant images. And so each time through the loop, the ith item is going to become the output of this imRead function. And we're going to give it the ith file name, right? So consonant images has our file names in it. When I is 1, that's going to be the first file name. So we're going to use imRead to read in the information in that file and put that into this cell matrix, right? And so then I'll save the next thing for later. So one little thing I haven't showed you guys to do yet, I don't think. Let's just clear out everything in the command line. One nice little thing about Matlab, is the integration between the editor and the command line. So one cool thing is if you want to test out some code, you can do something like this. You can highlight some code and say evaluate selection. And it basically types it in on the command line for you. So if I want to create that consonant images cell matrix that has our 3 file names in it, I can just do that by right-clicking that line of code. And then what I can do if I want to see if this is working or what it's going to produce, I can just highlight this code, right? Because all that depends on is that I've defined this consonant images variable. And look at that. So now I've got my consonant image cells. And it tells me what I'm going to end up with is a 3-item cell matrix, each of which has a 300 by 300 by 3 uint8 matrix. So what it's apparently doing is it's reading these PNG files into, even though they're in grayscale, I guess it's reading them into full color image format matrices, right? So if I want to show one of them, I can just use IMShow consonant image cells. Let's do the first one, which should be the B sound, I think. Yeah, so there it is, right? Kind of cool. If I want to show the second one, just do that. So that shows us what we're going to get out of that line of code, right? And it also shows you guys the little trick where, now of course, it gets more complicated to do more than a few lines of code to try in the command line, because of course any variables you refer to have to be defined and so forth. But if you just want to try out like 5 or 6 lines of code on the command line, it's nice to be able to highlight them and just say, do this right now on the command line. Evaluate selection is what you do there. Okay, so that's going to read in all of our consonant images so that we now have them stored and we can mix and match them as we please. But what we also have to do is read in vowel, let's call this vowel image matrix or something like that. And that's going to be, the variable is called vowel image, so let's call that, or let's do imRead vowel image. Right? And again, if we want to see what that's like in action, we can evaluate that to make sure we've got a variable called vowel image. Evaluate this to make sure it's read in. Now we've got vowel image matrix, which up here, it's a little cut off, but this is vowel image matrix, and it is also a 300 by 300 by 3 uint8 format. And if we want to show it, look at that, there's our vowel image, right? Okay. Now, of course, because we're using Psychtoolbox, we have to use something a little bit fancier than IMShow. IMShow is kind of, for quickie visualization, but Matlab is not particularly good at doing image showing very quickly or anything, so we have to use Psychtoolbox if we really want to do proper animation here. Okay, so I think we've got pretty much everything we need to do except what we actually need to do during the trials. So one thing we'll do, we're no longer going to be displaying text on the screen, right? We're going to be showing images. So I'm going to replace text list with image list. And by the way, you notice Matlab will do this thing here, right, where it'll offer to let you rename all of the instances of that variable name at once. Sometimes that's useful, right, because if you just want to basically find and replace a variable name with another name, that's kind of cool. I can do that, although, so I hold Shift and hit Enter to do that. Now, I'm still going to have to change some things about how I use image list later on because it's going to be defined a little bit differently than the text was. But it's nice to know that if I'm looking to rename this variable everywhere, because it's really a list of images we showed, not a list of text we displayed. I've renamed all of it right there, so that's kind of cool. Okay, so let's go through here. So each time we go through the trial, we're going to get our sound constructed with our noise and everything. So that's all done. And what we're really going to want to do here, this gets a little tricky as to think about when to do this. So what we're doing is we make our sound. Oh, so here's something we're going to have to figure out to change also, right? So instead of text number, which was like whether to show the text ba, ga, or da, what we really want, I guess, is sound number or whatever. But let's call this a consonant number. And again, we can rename them all if we want, although we're probably going to use it a bit differently anyway. So really, we're going to want to randomly select b, d, or g, right? Because all of those are going to end up transforming into the same vowel, ah, right? But so we're going to select randomly which consonant to display on each trial and give that a consonant number, 1, 2, or 3. Remember, randi 3 just gives us a random integer between 1 and 3, right? Okay, so we'll do that to generate a random number to tell us which syllable we want. Let's see where I did this here. So we can do this here if we want. Where do we use this text again? We use it here. So we're not going to end up drawing formatted text at all, right? So we can get rid of that. We're going to replace that with some other stuff. So let's get rid of this text because we don't need that. Okay. So let's see, what else do we need to do here? So we figure out which consonant we're going to animate. We filled our audio buffer with the sound we made. We flipped the screen and waited a second just to have a second of blank screen. So at this point, what we did do previously here was draw some text and then flip the screen and start playing the sound, right? But now what we're going to want to do probably is actually take this out for the moment. And what we're probably going to want to do is start playing the sound, and instead of just waiting, well, we can still wait a certain amount of time, so let's put this down here. So we have a blank screen for 1 second, we start playing the sound, and then what we're going to want to do is do this little animation, right, before we pop up our choices of what to respond, right? So what we're going to need is a for loop, where we kind of loop through and display all the frames of animation we want to display, right? So we already defined a variable telling us in frames, right? So how many frames of images we have. So, and I've already used I. I like to use simple letters like I and J for my for loop counters if they're just kind of basic counters. So let's say for J equals 1 to n frames. So, you know, if we have 10 frames of animation, it'll do this 10 times. You know, if we have 20, it'll go through 20 times and so on. And so what we basically need to do is figure out how to animate or how to blend together two images. So to make life a little easier, maybe I'll actually define a couple other variables here. So let's say let's call this consonant image, which is basically the picture of, you know, the lip position for a consonant that we're using on this trial. And let's get consonant image cells number consonant number, right? So meaning that if consonant number is 1, this is going to be the image for ba. If consonant number is 2, this is going to be the image for da, and so on, right? So then we've got this consonant image in its own variable, which just is going to make this line of code a bit easier than it was in the version I sent you guys. You know, again, sometimes I like to squeeze everything into one line of code, and sometimes I like to unpack it a little bit to make it easier to read. So let's make it a little bit easier to read this time. So let's call this something like this frame image. I think I called it this image in the version I sent you guys, but again, let's make things a little bit more descriptive when we can. So what we really want to do, remember what we said is we want to start out with basically 100% the consonant and blend it frame by frame until we end up with an image that's 100% the vowel picture, right? So what we really want to do is we want to take our vowel image, and we have this list of image proportions, right? And it starts at 0 and goes to 1. So what we want to do is start out the vowel image at 0. So we're going to use image proportions and image proportions number j. So the first one, second one, so forth. So that's going to start at 0 for the vowel image, and each time through the loop it's going to multiply the vowel image by a higher frame number. So that'll start out multiplying the vowel image by 0 and end up multiplying it by 1. And add that to what we called this consonant image times, and then basically we want to do it times 1 minus that, right? So if the vowel image is 0%, we want consonant image to be 100%. If the vowel image is 10%, we want consonant image to be 90%, and so on, right? So it's just going to be times 1 minus image proportions j, right? So that's going to make a blended image, just like we made a blended sound. So now we're making blended images and blended sounds. And then one thing I think we talked about this briefly is we have to make this thing called a texture, right? So we have to say, like, a texture is basically, like we said, really what Psychtoolbox is doing is using your graphics card. And so, you know, graphics cards tend to think of the world as polygons, you know, like in your I mean, now with like a PlayStation 3 and Xbox 360, 3D animated games don't look like they have a lot of polygons in them. But if you think back to like Nintendo, were you guys alive when there was like a Nintendo 64, the first PlayStation, when 3D type games actually you could see the triangles, right? So like, back when 3D images in video games were actually made out of clearly triangles, right? So you either have like these triangular 3D images, or you have textures, right, which are flat images, right? So in this case, everything we're showing is a texture, a flat image. So, and it was called that because, again, what those were usually used for in graphics cards was to put textures on top of these like 3D images, right? So we use the make texture subfunction of screen and just give it our window and this frame image, and that basically takes that image information and puts it into a format that we can then tell screen to draw on the screen. And then what we can immediately do is tell screen to draw that texture on the screen. So that uses the draw texture subfunction of, again, this screen function that's like the one function to rule everything in Psychtoolbox for drawing stuff. Okay, so that draws it to that invisible background buffer. And then what we can actually do, and this is a good thing to do actually, is close the texture when we're done with it, because basically textures take up a fair amount of memory on your graphics card. So as soon as you're done drawing one, it's a good idea to close it unless you plan to use it again. And since we're changing the images that we're animating every single frame, there's no reason to keep it around. We can just kind of recreate them when we need them. So we'll close the texture. And one other minor thing, so one thing that we basically are then going to want to do is we're going to want to flip the screen, right? Because when we're done drawing everything, which is basically just that image, we're going to want to flip the window. But one other little thing I like to do in this code is, of course, we're going to need to know what time our trial began for the purposes of getting RT data, right? So we could do this a couple different ways. We could have just called our old friend the function getSex, like back here where we started the sound. But we could also get a timestamp of when the first frame of this animation comes on screen. So this flip subfunction will give us timing information, but we really only want to save the time the first frame came on screen, right? So what I really want to do is say if j equals 1, in other words, if we're on the first frame, we'll still call screen, but then we'll say, let's call this like stem onset time, because I think that's what we called it before. And otherwise, just do a plain old flip. Does that kind of make sense? So that saves the timestamp of when our first frame was flipped. If it's not the first frame, we just flip without saving the timestamp. And then down here, if you remember, when we get a response, we get a key time. When we calculate our, RTs, we take key time minus the stem onset time, right? And that gives us our RT. So now we're saving our stimulus onset time. So that's good. And that might be it. So the only other thing to note here is that, I think I mentioned this before, you can tell the flip function when to flip if you want to. But if you don't tell it when to flip, it basically says flip right now. But remember, right now means the next time the screen redraws itself, right? So hopefully what we're going to do is it's going to take us less than one screen frames amount of time to do the stuff in this loop, right? So if we're refreshing at 60 hertz, we get about 16 milliseconds of computing time each frame. So if we can do these, 5 or 6 calculations in 16 milliseconds, which should not be too hard to do, basically what's going to happen is this is going to, flip a new frame every screen refresh, right? So it should actually take, the same number of screen frames as our times through this loop. Now, if we were trying to do something really complicated in here, it could slow down the loop a bit so that your image actually animates too slowly. But I think we'll be all right with this. So I think, unless I'm forgetting something, I think that's all we need to do to make this work. So let's try this. So again, watch out for loud noises. There's probably some typos or something. Watch it crash.
No.
Yep. Okay. So what did I do wrong here? Line 90. Oh, okay. Interesting. Val image. Is there this constant image? Integers can only be combined with integers of the same class or scalar doubles. Oh, just see how, before I think I see the problem, but let me, okay. I see the problem. Okay, so this is a problem that's going to go away when we do our other step, which is why I didn't have it in my original code. But just to sort of see what the issue is. So we have our vowel image matrix. Like again, if we, so I've still got this loaded into the command line. So remember, we just as a demo, we loaded in our vowel image matrix. Right, it looks like that. So if we want to like make that 50% as bright, let's call this just vowel 2 or something like that, equals vowel image matrix times 0.5. All right, so what we notice is vowel, okay, well vowel 2 should still be 300 by 300 by 3 uint 8. Oh, that's interesting. So if we see that, like what we basically did if we multiply it by 0.5 is we made it darker, right? Because we make the brightness half all the way around. But that's interesting that it's still a uint 8. Let me just check something here. It might depend on the order that we put things. No, that's all right. Let's try something else. Well, no, I don't see why that would actually cause a problem. So let's try this. When in doubt, have I shown you guys this trick before? I don't know if I have. I don't necessarily recommend you guys use this, but this is another shout out to good old Kraus. If you have a bug in your script, and what you might ideally want is to go into the Matlab debugger whenever you encounter an error. There's this little command you can use called dbstop if error, and what that basically does is say, I don't want to set like a breakpoint in my debugger. I don't want to like step through every line of code, but if any errors get encountered, stop and let me go into the debugger and figure out what all the variables are. So let's try the McGurk demo. Now the problem is, what that's going to do is it's going to have the error and then it's going to freeze my screen, and I'm going to have to do that trick where I clear out Psychtoolbox. So and it may or may not work. Oh, I may have just crashed Psychtoolbox again. All right, so there goes Matlab. Let's try that again. That's the downside of dbstop if error. Actually, the other thing I can't, no, that's all right. Let's try that again just the way it was, but hopefully this time I'll be able to quit it without crashing everything. Okay, so let's try that again. All right, so there's our error. Okay, no, it really doesn't like stopping the code there for some reason. So let's do this instead. So we know where the error is happening. So what I'm going to do instead here is do the trick that I did before that I forgot we did last week, which is why I was having trouble at the beginning of this lecture, which is I know the error is going to occur here on line, what did I say, 90? So I'm going to set a breakpoint there and call PFP PTB cleanup to sort of get rid of all the Psychtoolbox stuff and then look at all my variables and things before that line that would crash the code. Okay, so here's the line that's going to cause us trouble. So we've got vowel, oh! Well, this is just dumb. I used the wrong variable, right? All that trouble. And I just forgot to use, instead of, because I think I did call it vowel image in the old text. It's called vowel image matrix. And that should be all I have to do. The joy of live debugging. All right. But again, I think it's good for you guys to kind of see how this process works because, I mean, I'm sure if you do any more programming, if you haven't run into this already, a lot of times you'll spend half an hour tracking down what you think is some really complicated bug, and it ends up just being a typo somewhere, or you call something the wrong name. Yay! Ga. Da. So you see we've got this little ghetto animation here. Right? Ga. Alright, so that kind of works, right? I mean, again, it's a little silly, but apparently it does work on me, actually. The illusion does work on me, as I found out last night. And it seems like what we did worked, in that seems like it takes about the same amount of time to display the image as it does, to play the sound, right? Which is what our goal was. Now, if I want to just prove it to you that, like, if we do something really slow in this loop, like I said, we could have the image take longer than, you know, that to play. Let's say we just did something really kind of stupid, like let's wait 18, oh no, that's 180 milliseconds. Let's wait 18 milliseconds, which is just more than one frame time. This should make the animation take about twice as long as it does. So it should take about twice as long as the sound now. Just to sort of prove that idea that you have to watch out how much you do if you're animating every frame. Right? See how that slows it down by a factor of about 2? Because we're deliberately taking an extra frame doing nothing to animate slower. Okay, so I'm going to quit that because that gets annoying real quick. I'm just going to clear things out. Okay, so the only other thing we really wanted to do with this task, if that all, does that kind of make sense? Anybody got questions on how we did that so far? How we blended those images together? So the only other thing we said we might want to do is, you see it looks like, it kind of looks like the animation works, but it kind of looks a little bit funky. One thing we might want to do to just kind of make it look a little bit smoother is just to literally smooth out or blur out the images. And this is a little bit more of a sophisticated thing to do, so I don't think you really have to understand what we're doing here, but I will kind of quickly walk you through it. So there's something called, so if you want to blur something in Matlab, there's an operator to do it, but what you really are doing is applying a filter. It's called a filter to the image. It's sort of like if you guys have used Photoshop, there are filters for blurring and filters for sharpening and filters for making something look like it was written in colored pencil and all kinds of things, right? So Matlab will do all the same stuff for you that Photoshop will. And if you're a real nerd, you know, which I will confess to being sometimes, you can do a lot of the same things you do in Photoshop in Matlab to an image, but with much finer control because you can adjust the exact numerical values of what you want to do. So what we really need to do if we want to blur out an image is we need to tell it, some things about how to create a blurring filter with the right amount of blur to it, and then apply that to each of our images when we read them in. So what you need to tell Matlab if you do want to make a blur filter, and it's called, what I called it here is smoothing kernel, because really when people blur stuff, they really call it smoothing an image, but it's the same idea. So you need to tell Matlab the size of it, which is in pixels. So basically, it's just like in Photoshop, selecting a bigger brush if you use the blur tool blurs things more. And similarly, you need to tell it something like the standard deviation. That's what SD stands for. Again, that's in pixels, I believe. Actually, let's not say that because I'm not even sure what the units are of that. That you can kind of think of that as like being sort of the strength of your blurring brush, kind of. So these two different ways that you can make more or less blurring happen. You can kind of figure these out by trial and error. We can tweak these once we get the code working to see how those affect things. Okay, so basically what we want to do is we've defined basically the parameters up at the top of our smoothing filter, or our blurring filter. So what we can do is go down here to where we first start reading in our images. And what we have to do is tell Matlab to make us this filter, this image filter. So I called mine smoothing filter. And that's created using a function in Matlab called fspecial. And again, this is a little bit of black magic here. So Gaussian is basically another word for a blurring filter. So this is saying make a filter that is a Gaussian filter, a blurring filter. And again, if it makes sense for me to say this, what you're essentially doing, you guys know your normal curve from statistics, right? What you essentially do when you blur something is you take a normal curve, only you have to think of it as like a 3D kind of thing. So think about like an anthill or a sandcastle that's the shape of a Gaussian normal curve that kind of falls off like that, right? What you're doing is you're saying in 2 dimensions. So if the 2 dimensions of this 3-dimensional like hill are your x and your y of your image, and your 3rd dimension is like how much to take. Basically, what you're saying is around each pixel, make the new version of this pixel mostly like this much of its original value, and then this much of the values around it this far, and this much of the values around it this far, and this much of the values around it this far. Does that kind of make sense? So like each pixel is maybe like 90% its original value, and then maybe 10% the pixels immediately around it, and 5% the pixels immediately around those, and 2% the pixels immediately around those. And if you add those together, what you're basically doing is adding some of the information from the surrounding pixels to each individual pixel, and essentially what that does is make it look blurry. In other words, it blends together information from the local area with each pixel's original value. Okay, if that makes no sense, don't worry about it. That's why it's called a Gaussian, is because Gauss was the guy that invented the normal curve. That's a Gaussian curve, or a normal curve. All right, so you tell it you want a Gaussian filter, give it the size, which is an indicator of how blurry it gets, and the standard deviation, which is another indicator of how much it blurs. And I recommend just doing those via trial and error because that's how I do it. And basically what you have to do once you've created that filter is you just have to use it. And you would do that here. So right after I read in the consonant images, I'm going to replace the item I just read in with a filtered version of itself. So I'm going to use another Matlab function called ImFilter, which is to filter an image. And you just have to tell it what you're filtering. So it'll be consonant image cells I. So in other words, we're going to filter what we just read in with the smoothing filter we just defined. And we do tell it this other thing called circular, which basically indicates tells Matlab what to do with the edges. Because basically if you blur something, you actually end up with a slightly bigger image than you did before. Because if you blur the outer edge of something, you end up with this blurry mess that goes further than the original image. Circular tells MATLAB to do the right thing, which is to kind of cut off, well, it kind of cuts off the image at the outsides. Just we'll say that that's what it does. But anyway, so what we're doing is creating a filter, using that filter. So now we're making each consonant image a blurry version of itself. And then we're just going to do the same thing to our vowel image matrix. This line of code is probably a little more clear because we don't have to worry about unpacking that cell matrix. So we're just going to call IMFilter on the vowel image matrix using our smoothing filter that we defined and telling it to do it circularly, which means we want to end up with an image the same size as the original. All right, so now that should be everything, because if we blur it once when we first read in the images, then it'll stay blurred, and then when we blend them all together, they'll be blurred. I've said blur too many times now, it doesn't sound like a word anymore. Blur. So now what we should get is just a slightly blurred face. Hey! And see, it looks a little bit more convincing, I think, if it's blurred out a bit. Right, because then it looks a bit more like an animation. Maybe it still doesn't look convincing to you, but at least according to my brain, it actually works in that, like, if you make it. So what I did last night that we might do next week, or we might just not worry about, is I made a version of this task that is precisely calibrated to give me sounds that I find ambiguous. So blend like da and ba together, exactly the right amount that I'm 50% chance at performance. And then if you play that blended ba and da together with either a ba or a da animation, at least for me, it did actually influence my behavior enough that I judged it to be more like ba when the image looked like ba, and more like da when it looked more like da. Okay, so we've got that working, and just to kind of show you a little bit about how these filter parameters work, let's make let's like nearly double the size of the kernel, and let's turn up the standard deviation also. So that should give us a much blurrier image, just to kind of show you how this stuff works. Right, so that gives us a much blurrier image, which may be useful for something. I mean, it gets, obviously, can get a bit extreme if you do much more than that. And that's really about it. And again, like, I think we're about at time, so I don't think we'll push the issue of like all the other stuff you could do. But you know, you could do all kinds of weird little things. Well, okay, I'll show you like maybe one weird little thing. See if there's an easy way for me to do this. So let's set back our blur values. Let's see if there's a... Well, I mean, so you can do something like... The easy things you can do, or you could like make a mirror image of something. Now, these are symmetrical, so it's not that helpful to do that. But we could do some kind of like, if you wanted to do some kind of weird image offset. Remember, these are just matrices. So let's say, I'm trying to think of a good way to do this. May not be able to do this. Okay, I think, okay, yeah, excellent. Okay, so this will be cool. It's not going to be that cool. But let's say, for example, this is just using another Matlab function. So what this does really is, let's say I have a bunch of random numbers. There's this circ shift function, which basically like shifts the values in the matrix. Let's say like shift by 2 positions. So what that does is, let's see if I did this right. So this will shift, like, see how 0.9282 was here? It shifts everything down 2, but it does it circularly, hence the circ, so that it goes where it went 0.9282, 0.7911, 0.2648, 0.3796. Now it goes down 2 positions, it goes 0.9282, 0.7911, 0.2648, goes back up for 0.3796, and so forth. So it shifted everything in the matrix down 2 positions, and the things that got bumped off the end get put back on the top, right? So if we wanted to do some weird thing where we like shift our image left and right or something like that, let me just check one thing. Okay, so let's pick a random number of pixels to shift our image down and to the right. Why we would do that, I don't know. Just for grins. Let's do shift horizontal equals randi size. So we're just going to do, we have to do it no more than the number of pixels in the image. So let's see, horizontal is 2. You don't have to exactly know what I'm doing here, but just to prove the idea that you can do anything to an image that you can do with a matrix. So right before we display the frame image, let's say this frame image equals circ shift this frame image. Let's see, shift vert shift horiz. I might have to add a 3rd dimension to that. Let's see if that crashes, because I think we do have a 3-dimensional image. All right, the details of this don't matter too much. This is just a dumb little demo of what else you could do. Oh, it worked. Okay, so we've randomly shifted over this image by a certain number of pixels, right? All right, so that didn't shift very much. Right, so what we're doing is moving it up, and you're basically tiling it, right? So moving it up or down or left or right a random number of pixels. Why you'd want to do that again, I don't know, but you know, that was just a couple lines of code that we added to do what looks like a relatively complex transformation, right? And again, if you wanted to flip the image, you know, do some kind of like distort it in some way, you can do all of those things with matrix math if you spend a little time kind of learning the sorts of things you can do with matrices, or just thinking about what you can do with them. Okay, so I think that's about it for today. So we've got to the end of this demo, which is awesome, because that was this is sort of our big accomplishment, I feel like, is we have now basically a full task in Matlab that does all kinds of crazy things, uses sound, uses images, dynamically changes them in real time, animates them, does all kinds of funky stuff, right? The only thing we haven't done yet is spit out a file, but I think we said we're just not going to bother doing that in Matlab. It's easy enough to do. It's basically the same way you do it in PsychoPy, so if anyone wants to know that, we can walk through it a bit. But yeah, so I mean, this is kind of the culmination, I think. I mean, it's not that exciting of a task, really, but it's kind of the culmination of our Matlab stuff. Because next time we're just going to play around a bit with like plotting data, showing you how to do some analysis and stuff. So it's a little more low-key, I think. And then 2 weeks from now, we'll do your projects. We'll work on your projects for the full 2 hours. Okay, so any questions about any of that? Hopefully you can, now feel free to play around with this yourself when you want. Hopefully some of this code will be very helpful to you working on your problem set. Hint, I think really all of the skills we practiced today will be useful for the problem set.